were discussing. Okay, good morning, class. Last time we were discussing that if you have a y, which is normally distributed with some parameter mu and covariance matrix sigma square, if you do some transformation of y, say cy or a prime y or ay or ay plus b, no? All of this still follows the normal distribution. And even if we partition y into these components where each of these are still vectors, then the conditional distribution at the marginal distribution of y1 is still normal, and the marginal distribution of y2 is still normal. Now we will look at the conditional distribution. Say, suppose you will still partition your y into y1 and y2, and you look at the conditional distribution, that is y1 given y2. Now the condition here is that your covariance matrix sigma, which was subdivided also into these partitions, no? The condition is that sigma 22 must be positive definite, because in the formula you have the existence of the inverse of sigma 22. So if sigma 22 is positive definite matrix, then the conditional distribution of y1 given y2 is given by this. So it is normally distributed, but the mean vector now will be in terms of mu1 plus sigma 21 times the inverse of sigma 22 times the difference y2 from y2 minus mu2. And the covariance matrix is equal to this term. Okay, so to prove that, so this is the assumption. This is the assumption. Now we will let x to be this term here. So if you look at that relative to this, so we see that y1 will have a mean vector mu1, and then so it is a function of this, no? Then mu2 sigma 1 2 sigma inverse 2 2, and then you have y2 there. Later the parameter will be y2 minus y1. So this is defined so that it can have this form later. And you have there your y2, so that we look at this vector now, x and y2 can be expressed in this matrix representation. Okay. So if you look at this, if this is how we define x, so pag multiply na to kana, that will be y1 minus sigma 1 2. So that is y1 minus sigma 1 2 sigma 2 to inverse y2. So this is 2 by 2, and this is 2 by 1. So the resulting here will be 2 by 1. No? So that is equal to that, and this is equal to y2. kana o kana. So this is actually the whole term here. This whole term is how we define X. No? So this is the importance of the assumption that sigma 2 is positive definite so that the inverse exists, so that n you can define this term here. No? So by theorem 3.6c, that is when you try to have, so if you have a y which is normally distributed and try to find out what is ay, this is still normally distributed and it has a parameter with respect to a, no? So if we find the distribution of this vector here, x, y2, then it is normally distributed with a, di ba ang ano, if you have y, which is normal, say mu sigma, then ay will be normal with parameter a mu, and then a sigma a prime, no? So your mu here, because this is your a, so this is your a mu. So your mu here is mu1, mu2, and your sigma star will be a sigma a prime. So if you find, if you multiply I, if you multiply I 0 minus sigma 1 to sigma 2 to inverse I, and then kato imuhang sigma 1 1, sigma 2 2, sigma 1 to sigma 2 1 here, and then the transpose of A, the transpose of A is I 0 minus sigma 1 2, sigma 2 to inverse I. If you multiply this, you will get this scenario here. So this is your sigma 1 1 relative to an AY, and then 0 as the sigma 1 2 or sigma 2 1, and then sigma 2 2. Now, you have a theorem. We have a theorem earlier na if this is 0, then most likely X and Y2 are independent, no? So naana siya sa theorem 3.7b. Okay, 0 man na siya. So it means that X and Y2 are independent. So it follows. So mo ni na statement, it follows. Because of this, no? It follows because of the value of this. Therefore, the conditional distribution of X given Y, so if we look at the conditional distribution of X given Y2, since X and Y2 are independent, is the same as the marginal distribution, no? So using the result of marginal distribution on the conditional distribution, you will have, so the conditional distribution of X given Y2 will be, unsa man ang imuhang X, so this will be equal to this one, kana siya. So kung imo nang i-multiply pa ana, what you will get is this one. And then this will be your sigma 1 1, or equivalently that is expressed in terms sigma 1 1 minus sigma 1 to sigma 2 to inverse sigma 2 1. So kini siya, ikuha na siya dinhi, no? After you multiply that. So since y2 is just a constant in the conditional distribution of x, so if we look at this, walay in terms of y2 din no? Sa imong conditional distribution. So it's just a constant with respect to the conditional distribution. Then we have, we can rewrite how we define x. We can rewrite it in terms of y1 so that you will have this after manipulation. So y1, this is how we define x, and then you solve for y1, balhin ang x. So you have this, no? Ang ato mang gusto is not, it is not the conditional distribution of x given y2. No, dili man kini atong concern, but our concern is the conditional distribution of y1 given y2. So since you already have the conditional distribution of x given y2, so you can rewrite x in terms of y1 and find the conditional distribution of y1 given y2. So what you will have is kay conditional distribution sa x given y2. So look at the difference. So you have y1 minus sigma 1 to sigma 2 to inverse y2. And then, so mao man na sa x, no? Muna pang x. And then you have this part. So what will be that part? That is a constant with respect to x. So y2, constant lang ni siya. So you write it back here. So it means that you have this as the mean vector for y1 given y2. You still have the same covariance matrix here. Or equivalently, after rearranging this or factor out sigma 1 to sigma 2 to inverse from this term, you will have this one, which is what we want to get. So theorem 3.7c tells us that if y1 and y2 are jointly multivariate normal, where sigma 1, 2 is not equal to 0, then the conditional distribution of y1 given y2, say if we have this conditional distribution, is still multivariate normal with bin vector given by this component and covariance matrix of the conditional distribution of y1 given y2 is given by this matrix. Now this result is very useful when you have when you apply it with actual data. Say, let's have this example. Suppose your y is normally distributed. 3 here means it's a 3x1 vector. A 3x1 vector with mean mu and their covariance matrix sigma. And so your mean is a 3x1 vector with entries 3, 1, 2, and this is your covariance matrix. So ibig sabihin kini siya mao ni ang sigma 1, 1, sigma 2, 2, and sigma 3, 3. The off diagonals are the covariances relation with other variables. So for x, for a linear combination of y1 and y2 and y3, we write it as x. So ang imong x is a linear combination of y1, y2, and y3. So particularly, we have y1 minus 2y2 plus y3. In matrix notation, getting your ay, no? Pwede mo na nimo isulat as ay, and that is just equal to a vector of constant, which is 1, negative 2, 1, 2y. So again, y is just the vector y1, y2, and y3. No? So if we multiply that, so vector naman siya, so that is A prime. It's not a matrix. So that is A prime. So recall na kung na kay y, na normally distributed with mean mu and sigma squared, sa gani ang A prime y is still normal with mean A prime mu and covariance matrix A prime sigma A. No? So that applying this concept, you will get A prime mu to be equal to, this is your mu. So your A prime is this. So what you have is 1, negative 2, 1 times 3, 1, 2. So matrix multiplication or vector multiplication will yield ini siya times that. That will be 3 minus 2 plus 2, which is just equal to 3. And you can solve for A sigma A and obtain 19. So kung actual data na ang A sigma A is 19. So this is your sigma. So what you do is you prime multiply this by A prime, negative 2, 1, and then post multiply it by A, 1, negative 2, 1. And solving that, solving A sigma A will give you 19. Hence, if your y is normally distributed with these parameters, no, then your x, which is y1 minus 2y2 plus y3 will be still normally be distributed with mean 3 and 19. Now, this is just of dimension 1 because what happens after multiplication, this is 1 by 3 and this is 3 by 1. This becomes a 1 by 1 matrix or just a scalar, no? So the parameter is 3 and 19 respectively. Okay, so let's have another example. Suppose you have two random variables which has different forms of linear combination. X1 is y1 minus y2 plus y3 and x2 is 3y1 plus y2 minus 2y3. And suppose you write your x as x1, x2. So this is partitioning of your matrix. So rewriting these two x1, x2 will have this matrix form or design matrix form. And this will be your AY. So for example, you have a y which is normal. What will happen to a y? Still normal with parameter a mu, and variance is a sigma a prime. No, if you recall from the results, so that a mu here will be 4, 6. That is after you multiply this matrix A to your mu will be mu1, mu2, mu3. with mu1 equal to 3. This is your mu1, mu2, mu3. With mu1 equal to 3, mu2 equal to 1, mu3 equal to 2. So after getting a mu, you will get a mu equal to 4, 6. And a sigma a prime multiplication with a and a prime and this given covariance matrix here, that will give you these entries, no? Which is 4. So here we see that since this is not equal to 0, then x1 and x2 are not independent. Okay, so with respect to marginal distribution, we use the derived formula earlier. So if we have y1 and y2 here, and y1 and y3, and we have this specific distribution. So where did you get that? Why can you say that y1 is normally distributed with mean 3 and covariance matrix 4 here? So particularly for y1, this is mu1 and this is your sigma 1, 1. So mo na ang distribution. So kang y2 kana, this is mu2, this is sigma 2, 2. Si y3, this is mu3, and this is sigma 3, 3. So si y1 is 3, 4, which is this. Si y2 is 1, 1, which is this. And si y3 is 2, 3, which is this. So all of this example has those matrix and vectors as its reference. So what we want is the marginal distribution or the joint distribution of y1 and y2. So this is the joint distribution of y1 and y2. You still get these entries here in your covariance matrix. So y1 and y2. y1 and y2 will be 3, 1, 3, 1. So mo ni siya 3, 1, no? And then the covariance matrix y1, y2 will be this part, no? So you have this one, okay? And then y1 and y3. So asa man si y1 ug y3. Si y1 ug si y3. So that is 3, 2. And y1, y3 except this. So you have 4, 2 and 2, 3. So here 4, 2 and 2, 3. Okay. So that is how you derive the particular vectors and matrices of your mean vector and covariance. And we see that since this is 0, then y1 and y2 are independent. However, since this is not 0, we cannot say the same thing with y1 and y3 about independence. Okay. Next, let's try to apply how to use the formula of the conditional distribution earlier. So what we want is we want the mu vector, the mean vector of the expected value of y given x. No? So this is mean. And then we use the formula of katong sigma 22 minus sigma 21 sigma 11 yy lang. So the given formula was sigma 11 minus sigma 12 sigma 22 inverse sigma 21, no? For your covariance matrix of y1 given y2, no? And the mean was equal to mu1 plus sigma 12 sigma 22 inverse, and then y2 minus mu2. Okay? So mga na ganina, no? This is the mean vector of the conditional distribution of y1 given y2. So applying that in this example, so suppose you have a random vector v, which is normally distributed with mean mu. The mean is equal to 2, 5, negative 2, 1, and the covariance matrix is equal to this. So for easy partition, so this part here will be sigma yy. This part here is sigma yx, sigma xy, and sigma xx. So that is we partition it in this manner, no? y1, y2. So ang ato ang v is y1, y2, and then x1, x2. So if we try to subdivide our mean vector here, so mo ni ang subdivision niya, no? 2, 5 ug negative 1, negative 2, 1. So 2, 5 and negative 2, 1. So your mu is subdivided as mu y and mu x. And this is how we subdivide our matrix, no? Kini siya. Okay? So this is 9001. This is negative 1. This is positive, this is negative. Kaya ang iya is 3, 3, negative 1, 2 man. Okay. 3, 3, negative 1, 2. So kini, ang row din may vector din kay ano man ni sila, symmetric. So negative 1, 2. So ibig sabihin, kulang negative. Dapat negative. Okay. So 3, 3 din negative 1, 2. Okay. So using the formula now, so atong formula sa conditional distribution, if we have y given y2, the mean vector of that is mu1 plus sigma 1, 2, sigma 2, 2 inverse y2 minus mu2. Okay, so that is your formula. So your mu1 here will be mu y. Kaya ang atong pag-subdivide sa atong v is y1, y2, kana siya, and then x1, x2. So the mean of that will be equal to 2 pi, the mean of y. No? So this is your mean of y, and this is your mean of x. So this is your sigma y x, sigma x inverse, and then you have this vector here. So that is y2 minus mu2, or equivalently in our notation, that is x minus mu x. So that if you do matrix multiplication here, you will arrive at this answer. And similarly, substitution of sigma yy and the following. So it is easy to find the inverse of a 2x2 matrix, no? So na ay formulaan na swap lang man na nimo. And then divide by the determinant. So you look at how to find the determinant, how to find the inverse of a 2x2. Sayon ra. Inverse of a 3x3 formula sayon pa, pero when you have greater large matrix, maglisod na mo kuwag inverse ana. Anyway, you will arrive at this. So let me call this mu star and this one a sigma star, so that V is normally distributed with mean mu star and sigma star. So that is the purpose of deriving this result here, because you can easily apply this when you have actual data. No? So this is the formula of the conditional distribution of y given x. So once you partition it, so this is the mean vector, so you just substitute it, and this is the covariance matrix. So that is how you apply the formula. Okay, so some remarks. If y is normally distributed with these parameters and your covariance matrix is positive definite, then y will have a non-singular multivariate distribution. So pag ang ato ang covariance matrix is positive definite non-singular. Otherwise, it will be a singular multivariate normal distribution. So another remark. So why the moment generating function is used in the development of the properties of the multivariate normal distribution. First, we cannot be assured that your sigma is positive definite. Because if it's not positive definite, then the distribution of y does not have a density function. And moment generating function is the natural tool to prove our theorems in 3.6 and 3.7. And a moment generating function allows us the possibility of a singular multi-normal distribution. So for your reading assignment, you read examples 1, 2, and 3 in pages 47 to 48 in Arnold. Now, let's go to another transformation of your y. So far, ang atong mga properties na gitud-an are just properties of linear functions of a random vector. Now, what happens when we have the product or in quadratic form ang ato ang y? For example, this is no summation here. Suppose we want the summation of yi square, no? Instead of in ani lang na forma, linear, it will be y times y. Or the y prime y, or the summation of yi squared, no? So what will be now the distribution when we have a random vector in quadratic form? So here, from normal, we will go to another type of distribution we call the chi-square distribution. Okay, in its derivation, recall, ang katubitang pag-derive nato sa atong y na normally distributed, no, with mean vector mu and atong sigma. Actually, sigma here was AA prime. We started there with a z, which is standard normal, no? And then we did a transformation on z, say a z plus mu, and arrived at this distribution. But it's still normal. Pero pag quadratic form na, we start with a standard normal distribution, say z1 from z2, and random samples means that the zi's are independent and each of the zi are normal. Then the vector, so kini individual values of the random variable, the zi's are normal. Then a random vector z, which composes of normal distribution, will still be normal with a mean vector 0 and the identity matrix. So identity matrix 1, 1, 1 sa diagonal. Of diagonals are 0. Ibig sabihin, all of the variances there in the diagonal are equal to 1. So if we define the summation of zi squared, I from 1 to, or that is z prime. So pareha man na z prime, z1, z2 to zn times z1, z2 to zn. So i-multiply na nimo, that will be the summation of zi squared. And that will be chi-square distributed. Okay? The 0 here indicates that it's a central chi-square. So in other words, we make this in English form, then the sum of squares of n independent random n independent standard normal random variables is chi-square distributed with n degrees of freedom. So associated with a chi-square distribution is a degree of freedom or degrees of freedom. Okay, since the moment generating function of a particular distribution is unique, then you can see that if your, say, psi is, if your random variable psi is chi-square distributed, here, dapat kini siya na siya din this is central. Ang atong notation manggod sa chi-square dapat ani, no? Na din ang degrees of freedom. Chi-square, degrees of freedom din and then here is a centrality parameter. We call it delta. So if it is just a simple chi-square degrees of freedom without the parenthesis there or with the parenthesis 0, it means that it is a central chi-square. Otherwise, it will have a delta here, which is a non-centrality parameter. So if it is central with n degrees of freedom, then the expected value of your random variable which is chi-square distributed, is equal to the degrees of freedom. And the variance of your chi-square distributed random variable will be twice the degrees of freedom. So ang expected value sa chi-square distributed na random variable is equal to its degrees of freedom, and the variance is equal to twice the degrees of freedom. And this is the unique moment generating function. So that will be 1 over 1 minus 2t raised to the n minus t. So if you have a moment generating function that looks like that, this one, then you know that your random variable is quite chi-square distributed. Dahil man ang moment generating function sa normal. Okay? That was e to the mu prime t plus 1/2 of t prime sigma t. Okay? So mauna sa normal. Okay, so extension for that. So dinhi ganina ang non-central or ang central started with standard normal. Now suppose ang atong random variable dili standard normal. Say suppose you have x1 to xn independent random variables gihapon such that it is normally distributed with mean mu I and covariance matrix 1. Then your vector x1, x2, xn will become normal distributed. This is prime or ang patindog ana, no? It's still normal distributed with mean equal to mu, but your mu here ang forma ana kay mga mu i's man na. Your mu here is actually mu1, mu2 to mu n, no? Only pasabot na mu diha. Okay, each of them will have mu1, mu i's. So if you get x prime x, so gani ang x prime x, that is the summation of xi squared. That will not be equal to central chi-square, but the central chi-square will be kinina forma. So if you have y prime y, where y is x minus mu. So ang difference from, so ibig sabihin lang ani, kung gusto ka central chi-square, imong i-transform ning x by x minus mu. You subtract it, murag i-standardize siya, no? Subtract it from mu and then standardize. Kaya ang imuhang variance manggod 1 ra. So ang square root of that is still 1. So if you recall in your basic statistic course, kung naa kay x na normal, and then gusto na nimo i-standardize, diba z is equal to x minus mu over sigma. But this is the standard deviation. Correct? Di ba mao ni ang transformation for standardization? I-standardize nimo imong random variable. Pero dinhi man god mao nang ang sigma wala siya x minus mu. Wala siya x minus mu kay ang kada isa sa ilaha kay with variance raman, with variance 1 or standard deviation 1 raman siya. So divide na actually by its standard deviation, but since it's just 1, so mura siya x minus mu ra times x minus mu. Okay? So mao man ni ang usual nato na standardization formula. or you want to standardize, and it becomes standard normal with mean. So standard lang siya, central lang siya basta standard normal, no? Pero in general, it will not be central chi-square if it's not standard normal. So later in general, tawag nato ana, dili siya central, tangtango na nato ang ano. Tango na natong 0 diha. But we can write this as x prime x is chi-square siya, n, pero ang non-centrality parameter is mu prime mu. That will be equal to mu prime mu. So that will be your non-centrality parameter. So here, mo na siya may tabo, no? Mu prime mu delta. So let y be this one. Your x is not necessarily standard normal, and then you have mu prime mu to be delta. So then we say that y has a non-central now, chi-square, with n degrees of freedom and non-centrality parameter delta. And we write this one. So natay duha, pwede y is central on the condition that nagsugod ni siya ang atong y, which is x prime x, ang atong x is normal, no? Standard normal, 0, 1. Otherwise, it will not be central but non-central chi-square. Any questions so far?
None, ma'am.
None, ma'am.
Okay. So, this is the first result. Lemma 3.8. So, observe that you have a y which is normally distributed. Dili siya standard normal ha. It has a mean mu. And it has a covariance matrix sigma squared I. Sigma squared I, ang pasabot ana, ang diagonal nimo puro sigma, no? And off diagonals are 0. So that is how it is written. Kay multivariate naman ni siya. So kung sigma lang, ibig sabihin univariate to siya. You have to attach the identity matrix. Okay, so this is your vector of y. This is your prime lang na ako kay gipahigda man pagkasulat. And then you have or horizontal pagkasulat, and you have your mean vector here. Sigma square is just scalar. Okay, there is a very important assumptions for chi-square before you can conclude that it's a chi-square. Dapat each of the yi here are independent. And then each of the yi are normally distributed. So if you recall, the square norm of y is the inner product of y and y, but that is equal to y prime y, no? So the square norm of y over sigma or y prime y over sigma is equal, is chi-square distributed with, okay, divide maninimo og sigma squared, then this will be the non-centrality parameter, sigma squared. So mu prime mu. So relative to y prime mu, ang iyahang non-centrality parameter is mu prime mu. Okay, so to prove that, so importante ha, ang chi-square, chi-square na siya basta ang assumption nimo ang imong mga yi's are independent. Each of the yi here are normally distributed with mean mu 1. This is mu, not mu 1, but mu I sigma squared. Then to see the distribution of y prime y, we look at the moment generating function. So, ang moment generating function basta normal is e to the mu prime t. The product here is just for independence. And then, ang t prime sigma t will be, this will be exponent there. Kana siya kay sigma raman na siya. Sigma I actually man t prime t. But there. Okay. Kung individual ang t prime t naapay summation ti squared na siya, no? So the product here will give you the vector notation here, no? Kaya ang may tabuana kay EA times EB times so on so forth up to N. May mo man na siyang E to the A plus B plus C antod pila ka buok. N na sila ka buok. Okay? So this is actually the moment generating function for a normal random variable. Now you define y prime x, y prime y, or that is your summation of yi squared. Mu prime u is the summation of mu I squared. And then, so kung si y na to, normal, mu sigma I, so may tabo kang y over sigma. Mu over sigma, no? Okay, scalar naman ni. And then, so may tabo ka niya ni. Divide ni mo. It's mu I, man, i-divide po ni mo sigma. Sigma squared. Okay? So that by definition of chi-square, ang y prime y, maraming 1 na lang na siya, cancel out man na identity, mga 1s sa sulod. Remember, this is mu I ha, mga mu I. So in general, I na siya kung vector siya. So that y prime y is chi-square distributed with parameter mu prime mu. So divide nato og sigma square, ma-divide pud ang parameter by sigma square. Ang variance sa constant, mahimo man na siyang variance of a constant x is equal to c square variance of x, no? Or equivalently, you have that. So this is now a non-central chi-square. So unsay assumption sa non-central chi-square? Kinahanglan ka satisfied ding mga components din here to conclude. Before you conclude that it's a non-central chi-square, dapat normally distributed and dapat independent sila, no? And then kung mukuha ka sa quadratic form na y prime y, mahimo siyang chi-square. And this is the non-centrality parameter. So mahimo siyang chi-square mu prime mu ang non-centrality parameter. So kung naka-i-divide diha, mag-divide po ka ana diha sa non-centrality parameter. Okay. Now, this is the probability density function of your chi-square normal distribution. Pabaluman mo ani, this is the univariate, multivariate na counterpart sa atong univariate. Sa atong univariate, your density function is just equal to the square root of sigma 2 pi. 2 pi square root of sa ang univariate na counterpart. The square root of 2 pi sigma, no? 2 pi sigma, then e to the negative 1/2 x or y minus mu over sigma squared, di ba? Okay? O ni ang univariate counterpart. So ang kinina part din ni kanang y minus mu square mo ni si y minus mu prime y minus mu. And then si sigma squared will be, naman na sa denominator, will be sigma raised to the negative 1/2. No? Kaya atong notation sa sigma squared sa matrix kay sigma raman. And then this is the square root of 2 pi na ay n over 2 na siya because IID. So kung i-multiply nimo 1 over the square root of 2 pi n times, that will be the square root of 2 pi raised to the n, or equivalently that is 2 pi raised to the n over 2. And then sigma here is sigma to the 1/2. Okay, kining sigma din is actually the square root of sigma square. So makuha ra na ninyo kung familiar mo sa univariate na counterpart, i-extend lang ninyo sa multivariate na counterpart, but this time it's in terms of matrix notation or vector notation. So you just study how the proof of the probability density function for the normal for the univariate case, because the derivation there uses some Jacobian matrix. No, I think that will be discussed it should be discussed or already been discussed in your undergraduate statistical inference, no, or probability theory class. Okay. So the next theorem is theorem 3.11, 10. So this is the assumption. You have a positive definite matrix of your covariance matrix and your y is normally distributed. So what we are going to do is to transform y as y prime y, pero gi-insert ta nato og inverse. So y prime sigma inverse y. No? So what will be the distribution of that? So kung naa kay y, atong y prime y, divide nato og sigma square, constant lang. This is chi-square and then mu prime mu sigma square, no? So unsay mahitabo kung atong y prime sigma inverse y, or equivalently mura siya y prime y over sigma. Okay? So to prove that, so this will be your non-centrality parameter. It is chi-square with non-centrality parameter mu sigma inverse mu. So ang atong technique ani is unsa na variable pangutana nato ani. So ang atong pangutana is unsa na variable na kung atong multiply na y prime y, mahimo siyang y inverse sigma inverse y. So unsa man ang ato ang itsura ana na dapat ano siya, kung ang original ana is x prime x, na mahimo siya ani. So ang candidate ana is an x to be sigma raised to the 1/2 y, no? So kuha na to ang prime ana and then multiply by this. So may mo siyang x prime x or y prime y sa ato ang original kini, no? So atong y prime y. So ang kandidato ana is kini sigma raised to the negative 1/2 y then sigma raised to the 1/2. So multiply na nimo, mahimo na siyang y prime sigma inverse y. So this is the candidate of your variable para ex prime x, no? So in this particular labeling, na kay A diha na matrix, di ba? Y mu sigma man mangita kag AY, that is A mu then A sigma A prime, no? So mao na ang distribution. So sa atong x na equal to sigma inverse y, human i-transform nato as sigma inverse sigma raised to the negative 1/2 x. So ang ato ang parameter ani is still normal with sigma raised to the 1/2 mu, no? So this is your A mu. Kanang A mu nato dinhi. Our A mu there will be sigma raised to the 1/2 mu. And ang atong A sigma A prime will just be the identity. Why? Because ang atong A is raised to the 1/2 sigma, then ang atong A is sigma man. Sigma raised to the 1/2 and then sigma raised to the 1/2 prime. Pero maura man na siya raised to the 1/2 gihapon. So what you will have is this is raised to the 1. Negative 1/2 plus negative 1/2 is negative 1. So may mo na siyang identity, no? So you have this. This is just equal to sigma this is just equal to I and this is just equal to I, no? So in here we rewrite sigma as raised to the 1/2 raised to the 1/2, but that is just equal to I. So hence this is what your y is distributed. So take note, ang atong aim dapat ma-meet ang assumption ha. So ang chi-square, ma-meet na siya ang assumption if ang ato ang mga random variable is normal with mean mu and variance sigma square. So dinhi na example, ang ato ang y is normally distributed with this mean and variance is just I. So ibig sabihin ang puros 1 ra ang diagonal matrix. Ang atong mga sigma square diha is just equal to 1. And then kuhanin mo ang x prime x. We have this. And non-centrality parameter is mu prime mu. Pero ang atong mu kay A mu man kini, no? Which is equal to that. So ang atong non-centrality parameter is mu prime sigma inverse mu. So that by lemma 3.8, x prime x, where x was sigma raised to the 1/2 y, and then if you get x prime x, that is equal to y prime sigma inverse y, satisfy man tanan assumption na normal siya with parameter ini. Satisfy man na. So that it will be, the quadratic form of that will be equal to chi-square distributed, and this is your non-centrality parameter, no? A mu prime A mu, but your A here is sigma raised to the negative 1/2. Okay, so what will happen when you subtract y by mu? This becomes a central, no? Central na siya. And your transformation will be equal to this. Wali z prime z nimo, pero ang imong formaan na is raised to the sigma raised to the negative 1/2 y minus mu. So it becomes central. Because this transformation here will give you a standard normal na random variable. So kung standard normal ang imong random variable, and then kuhaon mo ang quadratic form, that will become central chi-square. Kung dili siya standard normal, naa siya particular mean, then it becomes a non-central with the parameter mu prime mu. Okay? And properties of chi-square are additive. So kumukuha kag sum of chi-squares, chi-square distributed, it's still chi-square, no? So sum of non-central chi-square will be non-central chi-square. Sum of central chi-square will be central chi-square. Okay, so if you started with a non-central chi-square, you get the sum. It's still a non-central chi-square. If you have a central chi-square, you get the sum of central chi-square. It's still a central chi-square. So, mo na yung mga properties. And then, we will continue on spherical normal distribution next meeting. Do you have questions? So, Esteban is really not here, no?